So while we're setting up, I can introduce Marija Kulaš, is that more or less the correct pronunciation, from the Fern Universität in Hagen, in Germany, who is going to give a talk entitled A Term Matching Algorithm and Substitution Generality.
And in particular, generality of the question of generality of substitutions, and I present a decision procedure for this. So when we have substitutions will be taken in the traditional view, and that is modeling substitutions as total mathematical functions, and being composed as any other functions. So that straightforward modeling has been put into some doubt in the 1990s when some examples of non-intuitive behavior appeared, and in particular in the question of generality of substitutions. So as an example, if we have a substitution replacing the variable x with the variable y, should it be considered more general than substituting x for a constant a? So intuitively, of course, we are just swapping one variable for another, so why shouldn't that be the same? But formally, the problem is the accepted definition of substitution generality is a bit tricky. So for sigma to be more general than theta, we require that there be a mediating substitution delta, which composed with sigma gives theta. Observe that I'm using the old order of application, so the substitutions will be applied from right to left, not in the meanwhile prevailing post-fixed way. So if we accept this definition of generality, and so far as I'm aware, there is no other, then this substitution is not going to be more general, right? In case that the meta variables x and y here point to different object variables. Some will be using only meta level in this talk, so no reference to object variables. So in that case, the generality will not hold as we would have expected. So how do we know this? We surely cannot try all substitutions for their being eligible to be this delta, but we can prove something. So assuming we have found such a delta and compose it with x to y, Well, in order to obtain as a result x to a, to the constant a, we would have to connect this y with y to a in delta. So in case y and x point to different things, we would have two bindings in our result instead of only one. So that's the reason. And well, however nice such custom-made proofs may be, I was wanting mechanization of this, so a decision procedure. And observe, we are speaking when well, more general or equally general, right? Because at least the general would be a mouthful, right? So method and results, matching of substitutions, we reduce to matching of terms, which is easier. For term matching, we provide a simple algorithm called TMAT. It was originally from a textbook of on the term rewriting called Therese in a non-deterministic form. And we made it one pass by accumulating the bindings using a more general representation of substitutions that we are suggesting called relaxed form. So that's about method and results. And now a bit terminology, generality of terms and generality of substitutions I've put on one slide to show the similarities and how far they actually go. Observe that I'm not using the same symbol for both, and I would be advising against such thing because they're not really analog, because in case of terms, we are applying this mediated substitution on the more general object, but in case of in case of terms, but in case of substitutions, we are composing it with the more general objects, and that's not the same. So the other part of terminology is relaxed co-representation. Well, normally substitutions are represented in a very restrictive way. Only non-fixed points are taken into account, and there must be only finitely many. So the whole rest, the infinitely many, are just being ignored. They are mapped to themselves, right? But that is not sufficient for all purposes. For example, if we have a term S which can be mapped to a term T, but we also want to account for all variables in S. So bookkeeping of variables, then we have to tolerate also that which I called, on lacking a better word, passive bindings. X goes to X, so nothing is changed. Right? That must be tolerated. So a definition would be that a relaxed core for a substitution is any finite variable pure superset of its core. I'm not talking about domain. That's another source of confusion. Every substitution is defined on all terms, right? So it's core in my vocabulary. So obviously that's not unique, but for any application we have a fixed relaxed cost, and for a symbol I'm using just D instead of DOM for core. Well, the main purpose why this relaxed form is being suggested is that placeholding which is enabled by relaxed form is vital importance when we build a substitution and the variable has been confirmed to be passive. Well, it is passive, but it is not free, so it may not be bound at some later point, something else. So looking about that, it's a bit surprising that relaxed form hasn't been introduced much earlier because it is implicitly used like forever, because when we compose substitutions, like in this animation, wow, he's doing everything at once. Wow. Sorry about that. That's out of my control. For some reason, it's the animation. Well, I kind of cannot. Well, let's try this. Skip the animation, right? Wow. And again, further. Well, but you've seen it, I suppose. So the variable x start at first was deactivated. It's no longer active, but it's keeping this place. So the binding x to y must be discarded. So it is passive, but it's not free. So that's the idea. And now to the promised algorithm, term matching or subsumption is the most basic kind of pattern matching, just purely symbolic. And the difference to unification is that a non-variable may not match variables, right? So if you look at the definition, it's generality, right? So a term matches or subsumes another one if it's more general. And the algorithm for term matching that I have been adapted a bit takes apart from the arguments from the two terms L and R for the purported more general and less general term, also an accumulator. That's a substitution in relaxed form, and output will be a possible matcher if the algorithm does not fail, a possible matcher of L and R that is extending the accumulator delta. So it has 4 rules. If L is a variable, and there is already some binding in the accumulator, but to something which is not the intended R, then we have divergence. We are trying to bind a variable to 2 different terms. Otherwise, we put it in the accumulator. Then a failure. The other 3 rules are handling the case of L not being a variable. If L is not a variable but R is, we have shrinkage failure because we are trying sort of to shrink a non-variable back into a variable, which is not possible with a mathematical function. The next failure is clash because if you have non-variables but with different outlines, it's the top level functor and the number of arguments, so predicate indicator in ISO standard. And the last rule handles 2 terms with the same outline, so we need to iterate the algorithm and update the accumulator as expected. Justification of this algorithm would be in 2 parts. If it stops with failure, there is no match of L and R extending delta. And it is based on 2 observations. If a function maps L to R, then it maps each subterm occurrence from L to a sibling in R. In my paper, I've put a compact visual definition of what it is, a subterm occurrence, and what it is to be a sibling. Basically, a pair of corresponding terms in corresponding subterm occurrences in 2 terms. The second observation, each time the mat is reinvoked and its arguments L and R, that should be dashes, because that need not be the same as at the beginning, denote a pair of siblings within the original term. So that justifies the first part. And the second part, the algorithm obviously always terminating, and if not with failure, then it produces substitution, which is a match of L and R, extending the accumulated delta. Well, in the paper I've put additive to delta. It's also correct, but it's an understatement because it's already added, it's already there. Right? That can be seen by structural induction, which is the native method for terms. So in addition, if we call this algorithm with the identical substitution, with the empty substitution, then the resulting match, its relaxed co is exactly the set of variables in the term L. So we say it's L focused, it's exactly the set of variables, and it's relevant for L. It's a notion by app, meaning no extraneous variables, only just that it's there. Well, perhaps the only case where we don't need any algorithm or proof to be sure that generality holds is if the left-hand term is well, empty or identical substitution. Then it's obvious according to definition. But what can we do in other cases? For example, substitution x to y compared to its extension x to y and y to x. Which one is more general? Is there an opinion on this? X to y or x to y and y to x? Back again, right? Please? The second one. Well, I would advocate, you're right. Well, renamings are always the most general, so that, yes, so that's the answer, and we will see later that it is also confirmed by the decision procedure. When I started with this, I thought it would be easier to try with refutation. So can we have a term, say W, which is a witness of non-generality? So a term such that if there can be no substitution, no mediated substitution delta, then it will become apparent from the instances of W by sigma and theta. And luckily, it's just simple. We just take all the active variables of sigma and theta, and that suffices. So we apply a term matching algorithm, for example, TMAT, on the respective instances. And well, if we get an impasse, then there is no the generality is refuted. Otherwise, so here we have also this decision procedure. We have the other part. Otherwise, a matcher is found. So the generality is confirmed. In short, the method consists of reduction. So the problem of generality of substitution reduced to generality of certain terms. And also, if the term matching succeeds with a substitution delta, then it is good enough for generality of substitutions as well. In practice, that would look like this. We put, for given substitutions, a triangular tableau. So in this case, the substitutions have active variables x and y. So that's what we have on top. The witness list, and on the slopes are the two substitutions respectively. So now we just have to fill in how they are mapping the witness term. In this case, sigma is producing yy, and theta is producing ay. So the question is, can we match the left-hand term on the right-hand one? Can we? well, it's not school, I know. We cannot, because y would have to be mapped into two different ways. But simultaneously, of course, right? Once it will be bound to A, and once it will be bound to itself, so that's not possible. There's divergence, and well, that's a negative example. By the way, if you switch the order of substitutions, we don't gain much. Those two are incomparable. So, positive examples. Well, the first is above is an example by Ept. XY we now know is not more general, surprisingly, than XI, but it is more general than its extension, XA to Y and Y to A as well. And here the diagram commutes, so that means that we obtain a substitution delta, which applied on the left-hand substitution produces the right-hand substitution. And the example below is, well, that what we had as a question. The renaming on the left side is indeed more general than the other. Then it's, well, reduction on the right. And here we also see that the produced substitution is really in the relaxed form because it has one passive pair here. Well, well, in view of diminished interest in foundational aspects of logic programming, a question might appear, why is this important? Well, at least a referee of my paper put that question, so I can point to a famous counterexample which falsified the long-standing formulation of the completeness theorem for SLD resolution that's been around since 78, 80 in the work of Robert Hill and Keith Clark. It can be still accessed in Keith Clark's thesis. It's there, and it has been taken over in Lloyd's textbook. Well, the idea is that, well, it's put in the following way: every correct answer substitution must be more specific, well, an instance of a computed answer substitution. Well, it's disproved with the counterexample by Hyping Cole, looking like this. We have this query and the program, and it can be seen that the only computed answer is x to f, y, z with distinct variables y, z. But a correct answer can also be x to f of AA. And as shown by Hyping Code, these two are not in the generality relation. It's also shown here with the witness term method that we also have here divergence, so it's not possible. The wording has been corrected, well, concerning Lloyd's textbook in 1993, there was a corrected printing on Springer Link. It's still there, this wording, but the correction went in the direction of using terms and not substitutions. So those answer substitutions are applied on the query, right? So now we have a easier problem, and also new concepts have been proposed, avoiding the need for substitutions when describing logic programming computations, or things like parallel composition to avoid the need for composition. What I'm trying to point out here, substitution generality, not that analogous to term generality, so it must be perhaps revisited, the name or something, because moderated substitution is involved in both And if generality goes both ways, so we have equigenerality, then the moderating subset must be renamed. That's as far as the semblance goes, but visually, more general terms are, well, smaller as trees, but more general substitution can be either, can have bigger cores, can have smaller cores. The case of bigger cores we've just seen with the verifier. And above all, the unfortunate choice of word instance when speaking about substitution, that's just not correct, because analogy to delta applied to a term S would be delta applied to substitution sigma, not delta composed with substitution sigma. But a substitution applied on another one is not always, of course, defined, and even if it is, the result is not the same as delta composed. So a piece is missing, so that would be delta inverse on the end. That would be needed. So it's a problematic choice of a name. So my conclusions on the last slide. Instead of ad hoc proof, substitution generality can be easily decided by term matching, reduce the term matching. New concepts like relaxed core, where fixed points are allowed, can help with bridging the gap between the traditional core representation and the meaning of substitution, which is defined everywhere, right? We cannot just ignore a big part of a function and expect that the rest will take care of all the needs and behave intuitively. So that's just the problem here, right? And well, as the last word, the terminology related to substitution should, in my opinion, be revisited. So words like generality, equivalence, instance, in talking about substitutions are a bit problematic and enriched. So that's all.
Thank you very much. Are there any questions? I have just one comment, really, because I remember a lot of controversy about substitutions and unifiers and the term lattice and so on in papers about logic programming in maybe 20 years ago, 30 years ago. And there was a lot of discussion about in the ISO standardization group for Prolog about the correct implementation of predicates like instance of, not only the implementation, but what should the correct results be. And in fact, there was a change made maybe 10 years ago to the definition of instance of in the Prolog ISO library. So maybe you should look at all those predicates in the term library of Prolog and check that they really are correct,
wow.
Because as you say, there are bugs in some of the foundational concepts of logic programming. So
that would be a tall order.
You should talk to Ulrich Neumerkel in Vienna about the Prolog standard for all these predicates to do with terms and substitutions. Any other comments? Well, let's thank Marija again. And just a few minutes late, but we'll start the next session.